Okay. So, hi everyone. So, good afternoon all. So, first of all, let me know whether audio and video is clear or not. So, first of all, let me know, is audio and video everything clear here? So, good afternoon all. So, first of all, let me know whether audio and video everything clear here? Is everything clear? Yes? Okay. So, I hope everything is clear here. I hope audio and video is everything is clear. I hope so. Right? Okay. So, in the previous session here, I have taken the previous session in Telugu language. So, there I have explained how to prepare for this subject electromagnetic theory for GATE 2022. So, what is the preparation strategy you have to follow for this subject, that is electromagnetic theory for GATE 2022. So, that is what I have discussed in the previous session. So, that session is mainly for Telugu students. So, I have explained everything in Telugu there. Okay. So, today onwards, so this is the first lecture here for a Dalton batch. So, this batch name is Dalton batch for GATE 2022. So, in this we are going to start with lecture 1 on electromagnetics. So, this is lecture 1 on electromagnetics here. See, previously in YouTube we have provided the playlist. You can go through that. So, in that playlist you will see electromagnetic theory, that is EM theory, electromagnetic theory lecture 1 to you will see lecture 6 here, lecture 1 to lecture 6. So, in these lectures from lecture 1 to lecture 6 I have covered the introduction part, and I have covered the basics of vectors and coordinate systems. So, up to coordinate systems I have covered from lecture 1 to lecture 6. So, we have made a playlist also. Okay. So, you can go through that. So, up till here I have covered up to coordinate system. So, from here onwards for Dalton batch for GATE 2022. So, from here onwards I am going to start again from lecture 1. So, that is I am going to start up to here coordinate systems is completed here. So, from here I am going to start del operator. Today I am going to start vector differential operator. So, if you want previous lectures you can go through this. So, here basics of vectors is covered and coordinate systems are covered. So, you can go through these lectures. So, after these topics we are starting a new topic today. So, that is vector differential operator, Okay. So, today's topic is vector differential operator, or we can simply say del operator, vector differential operator, or we can simply say del operator. Okay. Okay. So, shall we start here? Shall we start the lecture? Yes or no? Give some comments in chat box here. We must have some interaction with each other while teaching the subject. Okay. Okay. So, shall we start here? Okay, fine. So, I am going to start the lecture here. So, that is vector differential operator or del operator. Now, see here. So, first of all, how we are going to represent this vector differential operator mathematically. So, mathematically we are going to represent this vector differential operator mathematically. How we can represent here? So, del is identically equivalent to dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap. So, del del operator is represented in this manner here, that is dou by dou x ax cap plus dou by ay cap plus dou by dou z az cap. The units of this operator is nothing but per meter, or you can simply say meter inverse, right? Okay. So Anand Seemakurti, hi sir, hi Anand, hi. Okay. Okay. So you have requested, Anand, I think you have requested for playlist, right? Okay. So we have provided that playlist here. You can go through that if you want, right? Okay. 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 Anand, sir, please teach in new page every time so that it will be good instead of scrolling and teaching in same page. Okay, okay. So I will try to change that style from today onwards, right? Okay, no problem. Okay. So the units of this vector differential operator is per meter or meter inverse, here. Now see here. See, this vector differential operator is having what? Is having x component. This is x component, and this is nothing but what? Y component, and this is nothing but z component. So we have this operator is having x component, y component, and z component. So that means it is a vector. Yes or no? So a vector is going to have x component, y component, and z component. Now if you observe this x component here, this x component is a differential operator with respect to x. If you observe the y component, it is also a differential operator with respect to y. If you observe z component, it is also a differential operator with respect to z. So this operator is nothing but a vector. Why it is a vector? It is having x component, y component, and z component, and all these components are differential operators. This component is differential operator with respect to x, this is differential operator with respect to y, this is differential operator with respect to z, and hence they have named it as what? Vector differential operator, right? So it is a vector, and it is having differential operators, okay. So it is called as vector differential operator, and in general this symbol is called as del here. We generally call this symbol as del, and hence it is also called as what? It is also called as del operator, right? Okay. So this is vector differential operator here. Now see here. So in general, if I write any operator, if I simply represent any operator here, the operator itself doesn't have any meaning. See here, if I write simply plus here, plus, or if I write simply minus, or if I write simply into, and if I write simply divided by. So this is an operator, this is also an operator. All these are nothing but what? Operators only. So if I simply represent the operators like this, does it have any meaning here? Does the operators itself have any meaning? If I simply write plus, does it have any meaning? Or if I simply write minus, does it have any meaning? No. So simply if you write the operator, it doesn't have any meaning here. So when these operators are going to have some meaning, so whenever they operate on what? Whenever they operate on some operands. Now for example, if I take the operands as 3 plus 2 is equal to what? Is equal to 5. And here if I write 3 minus 2 is equal to what? 1. And here if I write 3 into 2 is equal to what? 6. And here if I write 3 divided by 2 is equal to what? Is equal to 1.5. Now it is having some meaningful operation or not? Yes or no? So all these are nothing but plus, minus, into, divided by are nothing but operators. Yes or no? Are nothing but operators, and this 3 here and 2 here are nothing but what? These are nothing but operands. Yes or no? So whenever operator operates on this operands, you are having some meaningful operation. So this operation 3 plus 2 is equal to 5. So this operation we call it as what? Addition operation. And 3 minus 2 is equal to 1. It is having some meaningful operation which we call it as subtraction. And this operation is called as multiplication. This operation is called as division. Understood? So whenever operator operates on operands, then it is going to have some meaningful operation. Otherwise, if you simply represent the operator, it doesn't have any meaning here. So in the same manner, here this is also nothing but what? This is also nothing but vector differential operator. Vector differential operator. So if you simply represent this operator, the operator itself doesn't have any meaning. The operator itself doesn't have any meaning. Yes or no? Until it has to operate on what? Until it has to operate on something. It has to operate on something. Here these operators are operating on operands, whereas our vector differential operator is going to operate on functions here. It is going to operate on functions, or specifically speaking, it is going to operate on spatial functions. Okay, so note down that point here. So what is that point here? Vector differential operator. Vector, or you can simply write, I can simply write del operator. Okay, so del operator is nothing but vector differential operator. So here I can simply write del operator. Del operator operates on a spatial function. It is going to operate on what here? It is going to operate on spatial function, or simply you can simply say function. So a del operator is going to operate on a function. So in general, that function is nothing but a spatial function. So what do you mean by this spatial function? What is the meaning of this spatial function? How it is going to operate? So all these things we are going to see here. Okay. So vector differential operator or del operator I have represented mathematically, and its units is per meter or meter inverse. So I have represented what is the purpose of this operator and operands and all these things. So the operator itself doesn't have any meaning until it operates on operands. Similarly, our vector differential operator also doesn't have any meaning until it operates on a function. So del operator is going to operate on what here? It is going to operate on a function. So that function in generally it is a spatial function, right? Okay, so we will see how it is going to operate on these functions and all those things we will see now, right? Okay. See here. Now I said del operator is going to operate on spatial functions. I said it is going to operate on spatial functions. So what do you mean by spatial functions here? What do you mean by spatial functions? See, if you are having some physical quantity here, that is distributed in space, Now you want to represent that distribution here. You want to represent how or in what manner that physical quantity is distributed in space. Okay, you are having some physical quantity and it is distributed in space. Now you want to represent how that physical quantity or in what manner that physical quantity is distributed in space. That can be represented by a function or not? Yes or no? That can be represented by a function. See, for example, if I consider some function f of x comma y comma z, is equal to let us say xyz here. If I represent some function like this, so it is nothing but what? It is a function of what? It is a function of spatial variables. And hence we can call this function as what? Spatial function. What is the purpose of the function here? The purpose of the function is to represent the distribution of any physical quantity in three-dimensional space. Yes or no? How that physical quantity is distributed in three-dimensional space, that can be represented with this function. If I represent simply xyz, so that means what here? The value of this function is going to change from one point to another point in this manner. Yes or no? See, if you go to 1 comma 1 comma 1, at that location this function value is going to be 1. If you go to 1 comma 2 comma 3, at that location the function value will become 6. Like that. How this physical quantity, this is, let us assume this is some physical quantity, how this physical quantity is distributed in 3-dimensional space, that can be represented in terms of what? In terms of function. Since this function is depending upon the spatial variables, we call it as what here? Spatial functions. We call it as spatial functions, right? Okay. Now this is spatial functions here. This is spatial functions. Right, these spatial functions can be categorized into two types. These spatial functions can be categorized into two types of functions. So one is what here? One is a scalar function. So spatial functions can be categorized into two types of functions. One is called as scalar functions, and another one is called as what here? Another one is called as vector functions. Another one is called as vector functions. So what do you mean by scalar function and what do you mean by vector function? What do you mean by scalar function and what do you mean by vector function? So what do you mean by scalar function here? What do you mean by scalar function? See, at each and every point in space here, if you consider at each and every point in space, if the function is having only magnitude but not direction, at each and every point in space, if the function is having only magnitude but not direction, then that type of function we call it as what here? We call it as scalar function. See, for example, I can consider, let us assume temperature here. Temperature is a scalar quantity or not? Yes or no? So let us assume I am giving the distribution of temperature, in 3-dimensional space. Let us assume the distribution of temperature, that is T of x comma y comma z is equal to, let us say this is xy square z degrees centigrade. Xy square z degrees centigrade. Yes or no? So this is called as what here? This is called as scalar function here. It is going to give you what? It is going to give you the temperature at each and every location in space. If you go to 1 comma 1 comma 1 location, at that location the temperature is 1 degree centigrade. If you go to 1 comma 4 comma 1 comma 2 comma 3, then you are going to get what? 1 comma 2 comma 3, that is 4 into 3, that is 12 degrees centigrade at that particular location. That means generally this function is going to give you what? Is going to give you how the temperature is distributed in 3-dimensional space. So at each and every point here, at each and every point in space, this function is going to have what? Is going to have only magnitude but not direction. Why here? This temperature is what? This temperature is a scalar quantity. This temperature is a scalar quantity, and hence at each and every point in space this function is going to have only magnitude but not direction. So those type of functions we call them as what here? Scalar functions, right? Okay, so next coming to vector functions here. So what do you mean by a vector function? What do you mean by vector function? So what do you mean by vector function here? See here, if you consider at each and every point in space here, this function is going to have both magnitude as well as what? As well as direction. At each and every point in space, this function is going to have both magnitude as well as direction. Then such type of functions we call them as what here? Vector functions. Such type of functions we call them as vector functions. See, for example, I can represent some function f bar. I can represent some function f bar of x comma y comma z. I can represent some function as f bar of x comma y comma z. So let us say this is some vector function. So I will give one example here. See here. Okay. So example, f bar of x comma y comma z. So in general, how this vector function will look like? See here. So I can represent this as some xyz ax cap plus 2x square y ay cap plus 2xy z square az cap, something like this. Okay, I can represent in this manner. So that means if you consider the x component of the vector function here, if you consider the x component of vector function, and if you consider the y component of vector function, and if you consider the z component of vector function, in general the x component of vector function and y component of vector function and z component of vector function are vector quantities here. In general, sorry, what I am saying, in general, the x component and y component and z component of vector functions of a vector function is a function of what? Is a function of x, y, z. Is a function of x, y, z. That means what I am saying here is, if you consider a vector function like this, if you consider a vector function like this, in general, the x component of this vector function, the x component of this vector function can be a function of what? Can be a function of x, y, z. And similarly, the y component of this vector function can be a function of what? Can be a function of x, y, z. Similarly, the z component of vector function can be a function of what? Can be a function of x, y, z. So this is called as a vector function. This is the example of vector function here. So whenever you are representing vector function, it is going to have x component, y component and z component. In general, the x component and y component and z component are functions of what? Are functions of x, y, z. X, y and z. Generally, the students will think that the x component is a function of only x, y component is a function of only y, z component is a function of only z. That is wrong here. Okay, so you should not write like that. Okay, in general, x component can be a function of x, y, z, y component can be a function of x, y, z, z component can be a function of x, y, z. Understood? Now, if you consider this function, at each and every point in space, this function is going to have what? This function is going to have what? This function is going to have both magnitude as well as what? As well as direction. Yes or no? If you substitute 1, 1, here in place of x, y, x, y, z, what you are going to get? So at 1, 1, 1, what you are going to get? You are going to get 1 into ax cap plus 2 into ay cap plus 2 into az cap. So at this point, this vector function is having what? Is having both magnitude and direction or not? This is a vector quantity or not? Yes or no? It is having both magnitude as well as direction at this point 1, 1, 1. Similarly, if you substitute another point, you are going to get another vector. Yes or no? So at each and every point in space, this function is going to have both magnitude as well as what? As well as direction. Understood? So that is called as vector function here. Now that is the difference between scalar function and vector function, right? Okay, yeah, fine. So I hope it is clear here. Yes or no? Okay, yeah. Next, see here. So here, so what I said here, this del operator is going to operate on function, is going to operate on spatial functions. It is going to operate on spatial functions. Yes or no? Okay. So this is del operator. So here I am writing here, this is del operator. So when it operates, it is going to operate on spatial function. This spatial functions can be what? Can be a scalar function, or it can be what? It can be a vector function. Okay. So when del operator operates on scalar function here. When del operator operates on scalar function, it results in what here? Scalar function, let us say f. Okay, so it results in what? It results in an operation called as gradient, which is represented by gradient of f. So when del operator operates on scalar function, the resultant operation, we call it as what here? Gradient. Okay, so we can represent that gradient as gradient of f. Okay, yeah. So when it operates on vector function, when it operates on vector function here. When it operates on vector function, let us say that is f bar. Let us say that is f bar. Let us say that is f bar here. Whenever it operates on a vector function, it is going to result in two operations here. It is going to result in two operations. So what are those operations here? So one operation, we call it as what here? We call it as divergence, and another operation, we call it as what here? Curl. So here we will represent divergence as del dot f bar, and here curl we can represent mathematically as del cross f bar. Understood? Okay, so when del operator operates on scalar function, it is going to result in an operation which is called as gradient, and when it operates on vector function, it is going to result in two operations. One operation is called as what here? Divergence, and another one is called as what? Is called as curl. Another one is called as curl. Now see here. Here del is nothing but a vector differential operator. Del is nothing but a vector differential operator, and here f is nothing but what? Scalar function. So here this is vector and this is scalar. You are just simply multiplying vector operator with what? With some scalar function. So what is the resultant here? Vector into scalar. Vector into scalar. You are going to get what? The resultant is nothing but a vector quantity. The resultant is nothing but a vector quantity. Right? Okay, now coming to divergence. So here this is a vector differential operator. This is vector differential operator, and f bar is also a vector function. So this is also a vector. F bar is vector and del is vector operator, and you are doing the dot product between this vector operator and vector function. So if you do the dot product between any two vector quantities, the resultant is nothing but what? The resultant is nothing but a scalar quantity. Yes or no? So the resultant of this operation is nothing but what? Is nothing but a scalar quantity. A scalar quantity. Right? Okay. Okay. Next, coming to curl. So here this is vector differential operator, and f bar is also vector function. So if you do the cross product between the vector differential operator and the vector function, we call that operation as what? Yeah, curl. So what is the resultant of this one? Here this is vector operator and this is what? This is also a vector function. So if you do the cross product between these two vectors, what you are going to get? Finally, the resultant is nothing but a vector quantity. So the resultant of this operation is nothing but what? Yeah, is nothing but a vector quantity. Right? Okay. So when it operates on scalar function, the resultant is a vector quantity, and when it operates on vector function, you are having two operations, that is divergence and curl. So divergence, the resultant of divergence is a scalar quantity, and the resultant of curl operation is nothing but a vector quantity. Is nothing but a vector quantity. Right? Okay. So is it clear here up till now? Yes or no? Is it clear up till now? Okay. So I hope it is crystal clear here. I hope it is crystal clear. Next. So now here we are having these three operations, that is gradient, divergence and curl. So these three operations are called as vector operations here. Gradient, divergence and curl are called as what here? Vector operations. So now we will see each and every operation in detail. So how to represent mathematically, and also we are going to see their physical interpretation, right? So both the things we are going to see here. So next, so first we will start with this gradient operation. So first we will start with this gradient operation, right? Okay. Okay. So gradient here. So we'll start with gradient operation. Let us say gradient of f. Gradient of f. So first I will give you mathematically how to represent this gradient. So then we will go for what? Then we will represent, then we will go for its physical interpretation, right? So gradient of f is equal to what? Is equivalent to, so del is nothing but dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap. So this del is multiplied by what? It is multiplied by f. So that is scalar function f. So if you multiply with f, what you are going to get? what you are going to get here? You are going to get dou f by dou x, ax cap plus what? Dou f by dou y, ay cap plus dou f by dou z, az cap. So this is the mathematical representation. This is the mathematical representation of gradient of f. This is the mathematical representation for gradient of f. For gradient of f. Okay. So now this is the mathematical representation of gradient of f here. So now we will see its physical interpretation here. Now we will see its physical interpretation. Okay. So physical interpretation. Physical interpretation of gradient. Physical interpretation of gradient. Right. Okay. Now see here. See here. Now let us consider a point here. Let us assume some scalar function here. Let us assume some scalar function is distributed in this region. Let us assume some scalar function is distributed in this region. So now I am considering at this point, I am considering the function. So let us say the function is f of x comma y comma z. Right. So at this particular point I am considering the function, that is f of x comma y comma z. Now one more point you have to remember that. This is very, very important here. See this gradient, divergence and curl, all are defined at a point here. All are defined at a point. So this is very, very important note here. This is very, very important note. So all these operations, gradient, divergence and curl, all these operations are defined at a point, Okay. So make a note here. Make a note of this point. Okay. So make a note here. This is note. So this is very, very important. Gradient operation, divergence operation and curl operation, all these vector operations are defined at what? Are defined at a point. Okay. Okay. Now coming here, so we are trying to see the physical interpretation of this gradient. Now see here, I am considering a function. Some scalar function is distributed here. So I am considering a point here. So let us say this point is f of x comma y comma z. The value of the function at this point is f of x comma y comma z something. Okay. Now here from this point I have moved to some other location here. From this location I have moved to some other location. Right. Now at this location the function is so f of x plus delta x. So let us assume I have moved at this location, the function is f of x comma y comma z. So from this point I have moved to this location. At this location the function is f of x plus delta x comma y plus delta y comma z plus delta z. That means I have moved to a different location here. From this point I have moved to a different location. So at that location the function is what? F of x plus delta x, y plus delta y, z plus delta z. Right. So the change in function here, as you move from this point to this point is nothing but I can represent this with what? I can represent this with del f like this. Yes or no? So this del f represents what here? The change in function as you move from x comma y comma z to a point x plus delta x, y plus delta y, z plus delta z. Right. Okay. Okay. So now see here. This delta f here. This delta f, how I can represent here? This delta f, how I can represent? See here. As I move from one point to another point, the change in function I am representing it as what? Delta f. Okay. So here as I move from here to here, you are having change in x, yes or no? Change in x, and also you are having change in y, and also you are having what? Change in z. Yes or no? So the function is varying along x, the function is varying along y, the function is also varying along z. Understood? So now I can represent the total change in function here. I can represent this total change in function as what? The change along x plus the change in function as you move along y plus the change in function as you move along z. Yes or no? Okay. See, or I can say this is the function now. So if I move, let us say this is x axis, let us assume this is y axis, and let us assume this is z axis here. So from this point, if I move along x direction here, so what you are going to get? If I move along x direction, you are going to get only change in the function will change only with respect to what? With respect to x. Yes or no? As you move along x, only x value is going to change, y value is not going to change, and z value is also not going to change. So here the change in function I can represent it as f of x plus delta x. Yes or no? Here it is f of x comma y comma z, and here it will become f of x plus delta x. There is no change in y, that means delta y is equal to 0. So you can simply represent y. There is no change in z, that is z. Similarly, if you move along y direction here, then I can represent the function as what here? F of x comma. If I move along y direction, the change will be only along y. There will be no change in x and z. So I can represent it as f of x comma y plus delta y comma z. Similarly, if I move along z direction, I can represent the function as what here? F of x comma y comma z plus delta z. Yes or no? So this change, as I move along x direction, I am going to get the change in function along x. If I move along y direction, I am getting the change in function along y. If I move along z direction, I am going to get the change in function along z. Right? If I move in some arbitrary direction, then I am going to get the change in x, the change in y, the change in z. Yes or no? So the overall change in function, I can represent it as what here? I can represent it as change in function along x plus the change in function along y plus change in function along z. Right? Okay. So I can represent this as, see here. Okay, so the change in function along x. What is the change in function along x here? I can represent this as f of x plus delta x comma y comma z minus of what? Minus of f of x comma y comma z. So I have moved from here to here. Along x direction. So this is going to give you the change in function along x. So the change in function along x is nothing but what? F of x plus delta x comma y comma z minus f of x comma y comma z. Yes or no? Okay. Plus I can represent it as what here? The change in function along y. How you can represent the change in function along y? That is f of x comma y plus delta y comma z minus what? Minus f of x comma y comma z. This is going to give you the change in function along y. Yes or no? Plus I can write the change in function along z. How I can write the change in function along z here? F of x comma y comma z plus delta z. Yes or no? Z plus delta z minus of f of x comma y comma z. So in this manner I can represent the change in function or not? So the change in function I can represent it as change in function along x plus change in function along y plus change in function along z. So is it clear here up till now? Yes or no? Yes or no here? Is it clear? Right. So here I have written change in function is equal to the change in x plus the change in y plus the change in z. The change in function along z. So in this manner I can represent. Now see here, what I can do here is, see here. Now if I make this delta f tends to 0 here, if I make this delta f tends to 0, then this change will also tend to what? Tend to 0. Yes or no? As delta f tends to 0. What do you mean by delta f tends to 0 here? If delta f tends to 0, that is the change in function is tending to 0, that means this delta x will tend to 0, delta y will tend to 0, delta z tend to 0. Yes or no here? So delta f tending to 0 means here delta x tends to 0, delta y tends to 0, delta z will also tend to 0. Understood? Okay. So now see here. Now if I make delta f tends to 0, if I make delta f tends to 0, so then on RHS side also you have to make delta x tends to 0, delta y tends to 0 and delta z tends to 0. Now see here, what I am going to do here, what I am going to do here is, see, I am dividing this with delta x here. I am dividing with this delta x and multiplying with delta x. And here I am dividing this change in function along y with respect to y and multiplying with delta y. Okay, here this is the change in function along z, so divided by, I am representing with change in z, that is delta z, multiplied by what? Multiplied by delta z. Now here delta f tends to 0, so this means what? This means delta x tends to 0, delta y tends to 0 and delta z will also tend to 0. Yes or no? So write that here. So limit delta x tends to 0, you are having f of x plus delta x comma y comma z minus f of x comma y comma z divided by delta x into delta x. Yes or no? Plus limit delta y tends to 0, f of x comma y plus delta y comma z minus f of x comma y comma z divided by what? Divided by delta y into delta y, plus limit delta z tends to 0, f of x comma y comma z plus delta z minus f of x comma y comma z divided by what? Divided by delta z multiplied by delta z. Right? Okay. Now if you observe here, limit delta x tends to 0, f of x plus delta x comma y comma z minus f of x comma y comma z can be represented as what here? It is just like what? It is just like f of x plus delta x minus f of x divided by what? Divided by delta x, limit delta x tends to 0. Yes or no here? Limit delta x tends to 0. See, there will be no change in y and z. Yes or no? So I can simply represent f of x plus delta x minus f of x by delta x as limit delta x tends to 0. So this can be represented as what? This can be represented as dou f by dou x or not? Yes or no here? As limit delta x tends to 0, f of x plus delta x comma y comma z minus f of x comma y comma z divided by delta x can be represented as what? Can be represented as dou f by dou x. So you can represent this as dou f by dou x. Why I am using partial differentiation? Because f is not only a function of x, it is a function of what? More than one variable, and hence I am representing with partial differentiation. So this can be represented as simply dou f by dou x. And here I said limit delta x tends to 0. So delta x tends to 0 here. As delta x tends to 0, you can represent it as what? You can represent it as dx or not? Yes or no? So delta x tends to 0 means what? You can represent this as simply dx. So the change in x is tending to 0, that means you can represent simply as dx. So dou f by dou x into dx here. Dou f by dou x into dx. Now if you consider similarly this one here, how you can represent this one, tell me? So limit delta y tends to 0, f of x comma y plus delta y comma z minus f of x comma y comma z divided by delta y multiplied by delta y. You can represent this as what? You can represent this as, I am writing directly here. So this one you can represent it as dou f by dou y. This one you can represent it as dou f by dou y multiplied by what? Delta y tending to 0. You can represent it as dy. So this term I can represent it as dou f by dou y into what? Into dy. Now this term here, similarly I can represent it as what here? This term I can similarly represent it as dou f by dou z. Into what? Into dz. Dou f by dou z into dz. So in this manner we can represent it or not? Yes or no here? Yes or no? Is it clear here up till now? Yes, Anand, is it clear? Okay. Okay, so see here, one more thing here. Here delta f tends to 0. Delta f tends to 0 means what here? The change in function f tends to 0. The change in function f tends to 0. You can represent this as what? You can simply represent this as df. You can simply represent this as df. Or you can simply represent this as dou f here. Dou f. Okay. So why we are using partial differentiation? Because the f is not only a function of one variable. It is a function of more than one variable. Right. So this delta f tends to 0. I can represent simply as dou f here. Dou f. Right. Now see here. So what we got here finally? What we got on LHS side, we are having dou f, that is equal to what? That is equal to, we got dou f by dou x into dx plus what? Plus dou f by dou y into dy plus dou f by dou z into dz. Right? Yes or no? Okay. Okay. So now how I can represent this one? See here. Now here I can represent this one as dou f by dou x into ax cap plus dou f by dou y into ay cap plus dou f by dou z into az cap. Right. So dot dx ax cap plus dy ay cap plus dz az cap. Can I represent in this manner here? Yes or no? See, if you do the dot product between these two, you are going to get the same expression or not. So this expression I can represent in this manner. Dou f by dou x ax cap plus dou f by dou y ay cap plus dou f by dou z az cap dot dx ax cap plus dy ay cap plus dz az cap. Right. So this dx ax cap plus dy ay cap plus dz az cap I am representing with small differential length, that is dl bar. This represents what? This represents a small differential length. So I am representing this total quantity as what? As simply dl bar. Right. Okay. So this is equivalent to what? This is equivalent to. Now here this term I can represent it as what here? This is nothing but what? This is nothing but gradient of f or not? This is the mathematical representation of gradient of f. So you can represent this as what? This is nothing but gradient of f. This is nothing but gradient of f, and here you are having dot product. So that means here dou f here, dou f is equal to what? Is equal to gradient of f dot what? Dot dl bar. Dot dl bar. Yes or no? So we can represent in this manner here. We can represent in this manner. Okay. So we got dou f is equal to gradient of f dot dl bar. Dot dl bar. Now see here, now see here, if you expand this dot product, what you are going to get? You are going to get gradient of f, right, into dl into what? Into cos theta, into cos theta. So dou f is equal to gradient of f into dl into cos theta. Now I can represent this as dou f by dou l. Dou f by dou l is equal to what? Is equal to gradient of f into cos theta. Gradient of f into cos theta. So when this dou f by dou l will be maximum here? When this dou f by dou l will be maximum? Tell me. When this dou f by dou l will be maximum? Tell me here. When this dou f by dou l will be maximum here? Respond. So this dou f by dou l, this dou f by dou l will be maximum when here, when theta is equal to what? When theta is equal to 0 degrees. When theta equal to 0 degrees, this dou f by dou l will be maximum. So dou f by dou l maximum is nothing but what? Is nothing but gradient of f. Gradient of f. Yes or no? So that means gradient of f is nothing but what here? Is nothing but dou f by dou l maximum. Dou f by dou l maximum. So that means the gradient of f is going to give you what here? Is going to give you is going to give you the maximum slope of the function, is going to give you the maximum slope of the function or the maximum change in function at a point. So I will explain in detail here, no problem. So here just it is going to give you that gradient of f is equal to dou f by dou L maximum. That means it represents what here? It represents the maximum slope of the function, maximum slope of the function at a point. Okay, so this is just mathematically I have proved this one here. So how we have represented gradient of f, and what is the meaning of gradient of f? I have proved it mathematically. Yes or no? Okay, so it represents the maximum slope of the function at a point. Now I will explain in detailed manner here what do you mean by this gradient and what are its advantages. All those things we will see here. Okay. See here. So write down a statement here. So gradient of a scalar function, at a point, gradient of a scalar function at a point results in a vector quantity. Gradient of a scalar function at a point results in a vector quantity, and it results in a vector quantity here, and that vector quantity, it means that vector quantity. So it points in a direction in which the scalar function increases maximally from that point. I will explain this here. So what I have told here, so gradient of a scalar function at a point results in a vector quantity. Whenever you try to determine the gradient of scalar function, it is going to result in a vector quantity, and that vector quantity is going to point in a direction in which the scalar function increases maximally, from that point. Okay, so this is the meaning of gradient here. So whenever you try to determine the gradient of a scalar function, it is going to result in a vector quantity, and that vector quantity is going to point in a direction in which that scalar function is increasing maximally. From that point. Okay, see here, I will explain this one. See here. Now let us consider a point here. Let us consider a point. So some scalar function is distributed here. So let us assume some point here. At this point, the function is, let us say, f of x comma y comma z. So here you are present here at this location, right? Now from this location here, from this point, in how many ways you can move here? From this point? From this point you can move in infinite number of ways or not. You can move in this direction, or you can move in this direction, or you can move in this direction, like that. Yes or no? So you are having infinite number of ways to move from this particular point here. Yes or no? Now see here. Now what I want to determine here is, suppose what I am doing here is, if I move from this point in this direction here, if I move from this point in this direction, right? So now I am going to determine what is the change in function, as I move along this direction. What is the change in function? How the function is changing as I move in this direction, right? Okay, so that change in function along this direction I am going to represent with a vector, because you are representing the change in function and also in which direction it is changing. Both you are representing. That means I am going to represent that with a vector here, So here this vector represents what here? This vector represents the change in function, f in this direction, So here the magnitude or the length of the vector, here the length of the vector represents the change in function here. The length of the vector represents magnitude of the the length of the vector represents the change in function. The length of the vector represents what here? Change in function. And this head of the vector here, head of the vector represents what here? Represents the direction in which it is changing, Okay, see what I am saying here is, from this point I am moving in a particular direction. So in that direction I am observing what is the change in function. In that particular direction, what is the change in function? So that I am representing that change in function in that particular direction, I am representing with a vector here, Then the length of that vector, or the magnitude of that vector is going to represent what? Is going to represent the change in function, and this head of the vector is representing the direction in which you are representing the change, Okay, so now see here. Now so this is the point I have considered. This is f of x comma y comma z. So let us assume in this direction I got the vector like this. Okay, so you know what do you mean by this vector? This vector represents the change in function along this particular direction. Now if I move in this direction, let us assume I am moving in this direction. Let us assume in this direction I am getting the change in function. Is more when compared to this direction. So I am going to represent that vector like this. Yes or no? I am going to represent this vector like this. So this vector represents what here? This vector represents the magnitude of this vector represents the change in function, and this head of the vector will represent what here? Will represent the direction in which this change is occurring. Right. Now similarly, let us assume I am moving in this direction here. Whenever I move in this direction, I am going to get some change in function. That change in function in this direction I am representing with this vector. So like that at each and every direction here, let us assume I have determined the change in function in each and every direction like this. Understood? Okay, so now in which direction I got the maximum change in function here? When compared to all the directions here, when compared to all the other directions, in which direction we are getting the change in function maximum? In which direction this function is changing maximally? So in this direction or not? Yes or no? Now I am interested to determine in which direction this function is changing maximally. Okay, I am interested to determine in which direction this function is changing maximally. I am not interested in all the other directions here. I am interested, or I want to determine in which direction this function is changing maximally. So if you observe this diagram, in this direction you are having the length of the vector is more. So that means the change in function in this direction is more when compared to all the other directions. Right. So I want to determine this direction in which this function is changing maximally. So we can determine this direction here. We can determine this direction with the help of what? With the help of gradient of f. So whenever you determine gradient of f at this particular location, it is going to give you this vector. Which is going to tell you that the direction in which this function is changing maximally. It is going to give you the direction in which the function is changing maximally. Right? Yes or no? Okay. Okay. So that means whenever you try to determine the gradient of a scalar function at any point, it is going to result in a vector quantity. And what that vector quantity will represent here? That vector quantity will give you the direction in which the function is increasing maximally from that point. So is this point clear here? Is this point clear? Yes or no? Good evening, Prince Sakla. Prince, good evening. Good evening here. Which one you want to repeat here? Which one you want to repeat? See, I have explained that. See, I want to determine the direction in which this vector function is changing maximally. So that can be given by what? That is given by gradient of f. Yes or no? So so if you try to determine gradient of any scalar function, then it is going to result in a vector quantity that is going to point in a direction in which the function is increasing maximally, right? Okay, so I hope it is clear here. Okay, so okay, so now I will give you a problem here. So with that, it is going to be crystal clear here. So write down the problem here. Write down. So in an auditorium. Write down the problem. In an auditorium, the temperature distribution. The temperature distribution is given by. Let us say T of x comma y comma z. Is equal to x square yz degrees centigrade. In an auditorium, the temperature distribution is given by T of x comma y comma z is equal to x square yz degrees centigrade. Right? Okay. Now a mosquito located at a point 1, 1, 1. A mosquito is located at a point 1, 1, decides to fly in a direction such that it has to get warmer. As soon as possible. As soon as possible. It has to get warmer as soon as possible. Then determine its direction. Okay, so what they are asking here? So in an auditorium, the temperature distribution is given by T of x comma y comma z is equal to what? X square yz degrees centigrade. So a mosquito located at a point 1, 1, 1. A mosquito located at a point 1, 1, 1 decides to fly in a direction such that it has to get warmer as soon as possible. warmer as soon as possible. Then determine its direction. So you are having an auditorium here. So in that auditorium, they have given the temperature distribution. How the temperature is distributed in that auditorium. So that's what they have given. So it is the temperature in that auditorium is varying as what here? Is varying as x square yz degrees centigrade. Right? Okay. So now in that auditorium, we are having a mosquito. A mosquito is located at a point 1, 1, So this is auditorium. They have given the temperature distribution, and at a particular point, you are having what? You are having a mosquito. So at what point it is located here? It is located at 1, 1. It is located at 1, 1. Now this mosquito decides to fly. In a direction such that it has to get warmer as soon as possible. That means in which direction it has to fly. Right. So it is located at 1, 1, in which direction it has to fly such that it has to get warmer as soon as possible. That means it has to move in which direction here? It has to move, if that mosquito moves in a direction in which there will be a maximum change in temperature. Then it is going to get what? It is going to get warmer as soon as possible. Yes or no here? Yes or no? Understood here? Okay. Yes or no here? So you want to determine the direction in which it has to fly so that it has to get warmer as soon as possible. So it is located at some location here, 1, 1. So from this location, in which direction it has to fly so that it has to get warmer as soon as possible. That means if suppose it flies in a direction in which the temperature is increasing maximally, then it is going to get what? It is going to get warmer as soon as possible or not? Yes or no? So that means here they are asking the direction in which it is increasing maximally. So if you try to determine the gradient of this temperature function here, at this particular point 1, 1, you are going to get what? You are going to get a vector. Yes or no? So that vector is going to have both magnitude as well as what? Direction. Yes or no? That magnitude represents what here? The magnitude represents the maximum change in function. Yes or no? And the head of the vector will represent what here? The direction in which this maximum change is occurring. Right. Now here they are asking only what? They are asking only direction. So what you have to do? You have to determine gradient of t here. So if you determine gradient of t, you are going to get what? You are going to get a vector quantity. Yes or no? Okay. So it is going to have both magnitude as well as what? Direction. They are asking what here? They are asking only direction. So that means you have to determine the unit vector. Of gradient. Yes or no? Direction is always represented by what? A unit vector. So what you have to determine? So direction, if you want the direction, what you have to do? You have to take gradient of t divided by what? Take the vector divided by what? Divided by its magnitude. So this is going to give you the direction in which it has to fly such that it has to get warmer as soon as possible. That means they are asking to determine gradient of t by magnitude of gradient of t. Yes or no? Yeah? Okay, that means you have to determine the unit vector along gradient of t, right? So how to determine here? Because they are asking only what? They are asking only direction here. Right? So now see here. So what is this gradient of t? Tell me. So t is nothing but x square yz degrees centigrade. So gradient of t, that is dou t by dou x ax cap plus what? Plus dou t by dou y ay cap plus what? Dou t by dou z az cap. So to take this temperature function, the total function, take this total function and differentiate with respect to x. You are going to get x component. If you take the total function and differentiate with respect to y, you will get y component. If you take the total function and differentiate with respect to z, you are going to get z component. So what you are going to get, tell me? So differentiate this total function with respect to x. What you will get? You will get 2xyz, 2xyz ax cap, plus differentiate this total function with respect to y. You will get x square z ay cap. Differentiate this total function with respect to z. What you will get here? X square y az cap. So this is gradient of t. This is gradient of t. Yes or no? Now you have to determine gradient of t at which point? At which point? 1 comma 1 comma 1, 1 comma 1 comma 1. So this is equal to what? What you are going to get here? 2ax cap plus ay cap plus what? Plus az cap, plus az cap. So gradient of t at 1 comma 1 comma 1 is giving a vector quantity. It is going to have both magnitude as well as direction. Now they are asking only direction. So what you have to do? You have to determine the unit vector, that is gradient of t 1 comma 1 comma 1 divided by what? Magnitude of gradient of t at 1 comma 1 comma 1. So if you do this, what you are going to get? You will get 2ax cap plus ay cap plus az cap divided by what? Divided by square root of 2 square plus 1 square plus 1 square, that is root 6. So this is the direction here. This is the direction in which the mosquito has to fly in order to get what? In order to get warmer as soon as possible. Right? Okay. So I hope this problem is clear here. Yes or no here? Yes or no? Okay. Here. So we will see some more applications. We will see some more applications of this gradient, and we will study some more things about this gradient in detail in the next session here. So with this, I am winding up the session for today. So tomorrow also we will continue with the del operator. So we will see some more applications of this gradient operation, and also we will see some more purposes, or what is the requirement of calculating this gradient and all. Okay, so all those things we will see in the next session here. Okay, so we will see some more applications of this gradient in the next session. Okay, so next lecture will be on del operator only. It will continue here, right? Okay, so I hope it is clear here. I hope up till now it is clear. Is it clear here up till now? Yes or no? Tell me here, is it clear up till now? Yes? Okay, yeah. So I am winding up the session now. So tomorrow we will see some more applications of gradient, and then after that we will see divergence and curl. All those things also we will see in the next sessions here. So today I am winding up the session with this. Okay, so we will meet tomorrow at the same time, exactly at 4 p.m. So until then, take care. Bye bye.